so we're going to look at roots of complex numbers. Today is the 18th. Okay, so before we do that, we'll just do a little bit of a recap, just to make sure you're okay with certain parts. If I've got a complex number, so this is a recap. So let's say, right, the complex number 3. Use one that will give me a nice value. Right. Hey Tyler. Okay, so let's write the complex number 1 plus root 3 I in the polar form and Euler form. Okay, so do you remember how to go about doing this?
I think the Euler form is one that I remember. That's the one with the, you draw the graph with the real and imaginary planes.
Yes.
Okay.
So if I draw it, so I'll go through it and you can just copy down. So we've got the real part. We've got the imaginary part. I'm going to draw this onto my axes, so it's 1 in the real direction, and then it's 3 in the imaginary. So my complex number looks something like that. Okay, and to put it into polar form first, we need to, so polar form, remember, is this form, so you've got r times cos theta plus I sine theta. And r is the
magnitude.
Yep. And theta is just the angle between the x-axis and the angle. Okay, so r is easy enough to work out because we can just do that using, yep, so r is, and that should be, sorry, root 3, shouldn't it? So r is square root of 3 squared plus 1 squared. R is the square root of 10. Yes, sorry, so it's 1 plus I root 3I. Sorry, 1 plus root 3I, so we're going root 3 up, so it's root 3 squared.
Oh, root 3 squared is 3, plus 1 squared is plus 1.
No, yeah, I've done that wrong. Yeah. So yeah, root 3 is 3, plus 1 is 4, so r is 2. Yes?
Yes.
All right, now to work out the angle, again, we think about this as a right angle triangle. We're going to use tan of the angle is equal to opposite. So this length is root 3 over the adjacent, which is 1. So theta is equal to, thinking of our triangles, So 1 root 3, 2, 60, opposite, yes. So theta is 60, which is pi over 3. So 1 plus root 3I is equal to 2 cos pi over 3 plus I sine pi over 3. And the shorthand way to write this, we could write it as 2 CIS pi over 3. Okay, so that's just the shorthand way of writing cos pi over 3 plus I sine pi over 3. And then in Euler form, all good, okay. So in Euler form then it's just 2 times e to the I pi over 3. Is that all okay?
Yes.
Okay, right. We said if we've got 2 complex numbers, so and just to kind of go back to this actually before we go on, if you always have to sketch this out, right? Because if it lies over here, you still need the angle between the x-axis and this one, okay? So you're working out the acute angle and then subtracting it from 180, and so on, yeah? Make sense? No? Do you want to try one?
Yeah, I remember you saying that, for example, if your real number was positive and your measuring number was negative,
yep,
you would like go all the way back.
Yeah, yeah. Or you could, so if it's like that, yeah?
Yeah.
You could go all the way around like that, so it would be 2 pi minus what the angle is. Or you could do minus what the angle is.
Yes.
Okay.
That as well.
So you could go the opposite direction. Right, so another recap. If I've got 2 numbers in polar form, so that's if z1 is equal to r1 cos theta 1 plus sine theta 1. And z2 is equal to r2 cos theta 2 plus I sine theta 2. What is z1 times z2? And what is z1 over z2? Did we do this before? No? Okay. Well, we can, okay, so we'll do it together, okay, just for to save time. So we're going to take all of this, we're going to multiply it by all of this, okay? So, I've got R1 multiplied by R2 multiplied by cos theta 1 plus I sine theta 1. no harm. So you have it. So I'm going to expand these two brackets. So this times this is just cos theta 1 times cos theta 2. I'll do that times that, so I get plus plus that times that. And then when I do this one times this one, it's going to turn into minus, yeah. Sine theta 1, sine theta 2. All right, and then what I'm going to do is I'm going to group together my real parts. So cos theta 1 cos theta 2 minus sine theta 1 sine theta 2, and then I've got my real part, so plus I okay? Right, and then we can spot that this is actually, I can write that using my addition formula for a trig function, so that's going to be cos theta 1 plus theta 2. That's just straight out of the formula booklet. Yep. And then the other one is also straight out of the formula booklet, also the addition formula. Sine theta 1 plus sine theta 2. Okay? So this makes it dead easy, because if you've got two complex numbers which you're multiplying together,
Skip all the middle
yeah,
part.
you can skip all the middle part, you just multiply the modulus parts together, add the angles together. Okay? Now for the second part, to do the division, what do you think the answer is going to be? Like looking at the answer for the multiply part, you had to make a guess at what you think the answer for this one's going to be.
I would say probably in R1 over R2.
Yep.
Cos CIS
Yep.
theta 1 minus theta 2.
Right, exactly. That's exactly what it's going to be. Okay, now to get there, we don't like having this part on the bottom. Okay, how are we going to get rid of it? So it might not be as obvious when I write it in that form. If I write it in the full form. I've got a complex number, and I've got i's in the bottom. How do you get rid of them? Multiply top and bottom by?
I have right. Multiply all from the 1.
Multiply it by 1? Well, so multiply by the conjugate of what's on the bottom.
Oh, okay.
Yep. And that'll get rid of the i's on the bottom. Okay, so you're going to multiply by cos theta 1 minus I sine theta 1, because that's the conjugate of the thing on the, sorry, and it should be 2, shouldn't it? And multiply this by it as well. So what I'll let you, so you do it exactly the same way, okay? I'm not going to do it now, I'll let you do that in your own time. You'll end up with, just like what you said, R1 over R2, CIS, theta 1, subtract theta 2. But you can work through that in your own time, okay? Let me know if you have any issues. Alright, the next thing. I'm pretty sure we did this. The Muffler's theorem, does that ring any bells? Yes, good. So recap on this. So the Muffler's theorem says we proved that as well using linear differential equations. Okay, so let's look at a particular example with using de Moivre's theorem. And this type of thing is really common in exam questions. So use, that's usually the last part in a complex numbers question if it's one of the final questions. Use the Muffler's theorem to derive expressions for cos of 4 theta and sine of 4 theta in terms of cos theta and sine theta. Okay, so what we have to do is we want an expression for cos of 4 theta in terms of cos theta and sine theta, okay, and then the same for sine of 4 theta. So we're going to start off with, just thinking about if I've got cos theta plus I sine theta, and if I raise all of this to the power of 4, what's that going to give me? So using the Muffler's theorem, it's to the power of 4, what can you do?
Cos to the power of, or cos, we'll have a 4 theta.
No. So look at what the rule is. If we're raising it to the power, just take the power down into the angle. So it's cos of 4 theta yep. Plus
I sine 4 theta.
yeah, I sine 4 theta. Alright, easy enough. Okay, so that's one way that we can expand it. Now the other way we can expand it is by using everybody's favorite binomial expansion. So if I'm going to expand this using binomial expansion, my first term is going to be cos to the power of 4 theta plus, it's going to be 4 times cos to the power of 3 theta times I sine theta. Yep. Plus, I could use my choose functions, but I just want to use something quick, so there we go. So it's going to be plus 6 cos squared theta sine squared theta times I squared, and that makes that become a negative, because it's negative I, so because it's positive I squared. Okay, then we've got plus, what are we back to, 4 again, 4 cos theta, it's going to be sine cubed, and I cubed is negative I, okay, right, so I need to change that to negative. And I'll put my I in. And then I've got sine to the 4. I to the 4 is positive 1.
Yes.
Yes. Just plus. Okay, so far? All right, so we've got these two expressions, these two things. We've got this one, we've got this thing, but these are both equal to each other, yep? Because they're both equal to, this is equal to this, because they're both cos theta plus I sine theta all to the power 4. So what we can do is we can put them equal to each other, but rather than just writing it all out, which will take a long time, what we're going to say is we're just going to equate real and imaginary parts, because that's all we're after. We want to find an expression for cos of 4 theta in terms of cos theta and sine theta. So I can see that cos of 4 theta, now is cos of 4 theta a real part or an imaginary part? It's a real part, so my real parts in all of this are, well, this is equal to cos to the power of 4 theta minus 6 cos squared theta sine squared theta plus sine to the 4 theta. Okay, so that's my expression now for cos of 4 theta in terms of cos theta and sine theta. And then I can do the same for the sine 4 theta, which is an imaginary part. So I just take those bits. I don't need to put the i's in. And that's a really kind of common question, being asked to do something like that. All right, is that okay? All right, so let's keep going. So if we've got something like this, C is equal to cos theta plus I sine theta. Show that 1 over z is equal to cos of theta minus I sine theta. Okay. Well, we know that 1 over z is the same as z to the power of. Right. And using the Mufflers, if I'm going to do z to the negative 1, all of this to the negative 1 is just going to be cos of negative 1 times theta plus I sine negative 1 times theta. Yep. Cos of negative theta is the same as?
Cos theta.
Good. It's symmetrical in the y-axis. And sine of negative theta is the same as?
Negative I sine theta.
Yes, negative I sine theta. There you go, we've shown it. But this is important because it leads to 2 important results, which we'll write down. And these 2 important results are z plus 1 over z is equal to 2 cos theta and the second important one, if I do z minus 1 over z. Okay, so those are two important results. Oh, yeah, I'll do an example showing why. And also, I should say, so just using the same results as before. If z to the n and 1 over z to the n is raised to the power, the only thing that changes is the angle gets multiplied by the n. Okay, so we'll start off using this result. So using z to the n plus 1 over, sorry, just using my mistake, just z plus 1 over z is equal to 2 cos. Sorry, I've written the question down wrong. My apologies. It should be minus. Okay. Sorry. Yep. So it's equal to 2 sine theta. Now I'm after sine cubed. So what do you think I'm going to do to both of these?
Cube one side.
Oh yeah, I'm going to cube both sides, okay? So I'm going to cube all of this. And I'm going to cube all of the right-hand side, and I get 8 sine theta cubed. Now, if I actually expand all of this using binomial expansion, I'm going to get z cubed minus z squared times 1 over z. And it should be 3z squared, because of the binomial expansion, plus 3z 1 over z squared minus 1 over z cubed. I know that all of this equals 8. Okay, so it's just using the binomial expansion on that. So then I can tidy it up. Okay. Now, this will hopefully look a bit better if I just rearrange my left-hand side. Finish it off. I know that z cubed minus 1 over z cubed, this is equal to. Is it 2 cos? So it's 1 minus. So looking back up here. Yeah. Sorry, just make sure you got that. So that's plus, this is minus, yeah. So I'm just rushing. Yeah, so 2. Sine 3 theta. This is minus 3 times z plus 1 over... Oh, what have we done? That times that gives me that. That times that gives me that. Got positive, negative, positive, negative.
You have positive 3 over z, but then a line of negative 3 times positive 1 over z. Which would be negative 3 over z.
Whereabouts, sorry? Oh yes, I'm looking at the wrong thing. Yes, so that should be negative. Yep. Thank you. So negative 3, yep, times negative 1 over z, positive 3 over z. And that is equal to 2 sine of theta. Which is 8 sine cubed theta. Alright, and we're after sine cubed theta. I'm just going to write it up here. I'm going to divide both sides by 8. Did I do that right? 3 2s are 6, yeah. So that's that minus all divided by 4. couple of minutes, just when everybody comes in, we'll look at the roots. And that's the last bit of complex numbers that we need to do. Okay, so roots of complex numbers. So we'll do this in steps, okay? So let's find the cube root of 2 plus 2i. Now, we did these kind of before, okay? We said if I have got 2 plus 2i, don't need to write this down, okay? And z is a complex number, so I've got a plus bi. And if I want to find the cube root, okay, so this is to the power of a third, then if I cube both sides, I'll get something like this. And then I would expand all this using binomial expansion, and I would equate the real parts and equate the imaginary parts, yep. And that'll be able to give me a value for a and b. However, with this method that I'm going to show you, it's a lot easier and quicker because it enables us to find any root. So we could find, like in that exam question, the 24th root, or yeah, however many roots we want. So this, we want to find the cube root of this. Now, if I'm finding the cube root, how many roots will there be? 3, okay. And if there's going to be 3, there's going to be, okay, yeah, there's going to be 3. So the way we go about it, your very first step always, step 1, change into polar form. Alright, so if you do that for me now, recording again. Okay, so once you get into polar form, we're going to, or step 2, is that we're going to add two pi n to the argument. So remember, the argument's just another word for the angle. Yep. And then we're going to raise to the required power. So we've got the reason why we add this 2 pi n will become clear whenever, no, let's write it out in full, whenever we find actual solutions. So I've got pi over 4, and I'm adding on 2 pi n. Okay? Now, yep, so that's what we've got at the minute. We need to find the cube root. So what I'm going to do is, so this essentially, I write this as 2 plus 2i. I want the cube root, so that's to the power of. cube root.
1 over 3.
Yep, 1 over 3. So I'm going to do the same over on this side. Put that to 1 over 3. And put this to 1 over 3. Okay. Now this is probably why it would have been easier to leave this as root 8, because root 8 is the same as 8 to the half, yeah? So 8 to the half to the 8 to the, 8 to the half to the power of a third is 8 to the, 1 over 6. Okay, so it would have actually been easier just to leave that. And then I can use de Moivre's theorem. I'm going to take the third and multiply everything in the angle by it, yep. So it becomes pi over 12 plus 2 pi n over 3 plus I sine pi over 12 plus 2 pi n over 3. This. So we choose 3 consecutive values for n, and we want to choose 3 because we want cube roots. So for square roots, we would choose 2 consecutive values. So we're going to let n equal -1. So I've got pi over 12 minus 2 pi over 3. So that's letting n equal -1, and then so that's 4. So that's -7 pi over 12. And then I've got plus I sine, and that's going to give me the same thing. Now the reason I like to pick a -1, because I know that the next one's going to be dead easy because it's n equals 0. So I get 8 to the 6th. Cos of pi over 12 plus I sine pi over 12. And then the last one, let n equal 1. So I get 8 to the power of the 6th. So pi over 12 plus 2 pi over 3. That's 9 pi over 12, which is 3 pi over 4. And that's it. Okay, those are our 3 roots. If we look at something called roots of unity. So roots of unity are basically we're finding complex roots of the number 1. So you know the square root of 1 is? Yeah, and? -1, okay. Square root of 1, you said, is 1 and -1. What's the cube root of 1? Just 1, right. But is it just 1? Because if we're finding the cube roots, how many roots should there be? 3. So we've got 1 is definitely 1, but there's going to be another 2 as well. And what can you tell me about these 2 then, obviously? Yep, they're going to be complex, yep. What about the fourth root of 1?
1 and -1.
1, -1, but I have to have 4 roots, so there's going to be another 2 complex ones, okay? So this is where this gets interesting, because we can work out these complex roots using this method, okay? So let's find the roots of unity of 1. Let's do the fourth root of 1. Sometimes this question will be phrased something like this as well. If z is equal to 1, no, it'll be phrased like this. So solve z to the 4 equals 1. Okay, so that's another way they could phrase this question. And that's how they phrased it in the question 11 in that pack, okay? Except I think they did it to like 24 or something. So, our first step is to do what? Yep, so we're going to put the number 1 in polar form. So if I'm putting this on my graph, there's no imaginary part. It's just all real, so it's going to lie over here. So what's r?
1.
And what's the angle?
0.
Right, so we can write 1 is equal to 1 times cos of 0 plus I sine of 0. You okay, Jesse? Okay, and that makes sense because cos of 0 is, and sine of 0 is, so that gets rid of the imaginary part, and you're just left with 1. So that makes perfect sense. So we want the fourth root, so I'm going to put this to the power of 4. I'm going to put all of this to the power of 4, but I also have to add on to my argument 2 pi n, okay? And I'm raising it to the power of 4, so it's all of that over 4. So I've kind of done that in 2 steps, so I hope that's okay.
I solved a question with 0.
Good. Keep going, you'll do more. The more you do, the more you'll solve. Okay. So now we need to let our value of n equal how many values? 4 in this case, and we definitely want one of them to be 0, so which values do you want to pick?
-1, 0, 1.
Yep, we could do that. And I should have said before, it doesn't actually matter what values you pick. If I pick 10, 11, 12, 13, we're going to get exactly the same answers. It's just that the cost of that angle, or the cost of that particular value, is the same as the cost of the one previous, if that makes sense. It doesn't matter yet, it's just going to repeat. But you want to pick small ones, so we said -1, okay? So our first answer is cos of -π/2 plus I sine of -π/2. Now let's actually just look at this, because we can. Cos of -π/2 is the same as? No. Well, is it? Yes, it is, because... Right, and cos of -π/2 is the same as cos of π/2. So this is 0. And sine of -π/2 is the same as negative I sine π/2, and sine of π/2, sine of 90 is 1, right? So I get, my first root is -I. And hopefully that makes sense. Well, it does make sense, because -I times -I times -I times -I, that gives me +1, that gives me +1, so that gives me 1. Yes. Is that okay? So -I is our first root. Our second one Are we okay? Need help, Jesse?
Yes, please. Can you tell me...
How's it? Okay, so when n equals 1, I've got cos of π/2 plus I sine π/2. Cos of 90 is 0. Sine of 90 is 1, so I get plus I. So I is another one, and that makes sense, because I to the power of 4 is equal to 1. And then when n equals 2, I get cos of pi cos of 180 degrees is... Nope. -1, right? Sine of 180 is 0, right? So we got -1. And that makes sense, because the fourth root, we would expect, like we said, we'd expect 1 and -1, but there has to be 4 roots, so I is the other one and -I is the other one.